Okay, thank you, Mr. Chair. Yeah, I'm going to present work that we did about 2 years ago, and that is we're trying to do or test a vulnerability assessment that was created or put in place by Engineers Canada under their PIVC framework that helps identifying risks to any sort of infrastructure related to climate change. And this is very broad, and I'm going to talk about the PIVC protocol a little bit later. And this was still in their evaluation stage. It is still actually in their evaluation, and the new versions have come up. And Highway 3 was one of the earlier tests that were tried within the permafrost environment. So I'm going to talk a little bit about Highway 3 for those that are not from here and haven't taken that roller coaster ride yet. I'm going to talk a little bit about the challenges obviously related to Highway 3 and what maintenance challenges there are. I'm going to introduce the PIVC vulnerability assessment and then some initial observation and followed by a conclusion. So the host of it was the Department of Transportation, and Greg Cousineau, he was very supportive of this project, and the partners were Engineers Canada that provided support and had the idea or came up with the whole protocol, and DGC Engineering did the work. And here's just an example of some of the sections along Highway 3. Now, I probably didn't have to show this map, but just in case you forgot where you are, here's Yellowknife, Northwest Territories, and here's a section of the highway that we looked at, which is in essence the last 100 kilometers of the highway leading into Yellowknife. So we're starting here from Reetzo or Bechico down here, that's the line, into Yellowknife. And we are in a discontinuous permafrost zone, and Steve Wolf's going to talk about all the permafrost in the area in a little bit more detail following my presentation. But it's also important to understand what's the history of this highway. It is, first of all, it's the gateway to the Tibetan-Katuitu Lake Winter Road, so it's of very important, it's of high economic importance to have this highway going and that we get the material up to Yellowknife. It's the only connection to the south on an all-weather road. It used to be a gravel road, and it was reconstructed between 1999 and 2006, so to get rid of a lot of the turns that were on the highway, so we straightened it, and to make it available for a speed of 100 kilometers an hour, so that's the design speed of the highway. Now, what were the problems related to that? I mean, first of all, it was reconstructed under the anticipation that the permafrost will be sustained to the greatest extent possible, and with a 20-year time frame. So that was kind of the design intent initially. But soon after it was completed, maintenance was just, I wouldn't say overwhelming, but the maintenance efforts were definitely much higher than anticipated. But on the other hand, it's not any different than other roads that we know from permafrost environments. We've noted with other roads that maintenance is key, and maintenance efforts are just increasing to a level that wasn't really acceptable, I guess, for the DOT anymore. This sketch just summarizes schematically the main problems that we have. I guess most of you are familiar with those problems. So we're generating thaw under the shoulders mostly that result into a shoulder rotation. That results in these longitudinal cracks. We have culverts. We have differential settlements along culverts. We get cracks, we get bumps. In winter, we have the snow accumulation again in the toes that result into further degradation in the shoulders. And this uneven permafrost degradation, that's really what's causing all the problems and the heterogeneity in the foundation that makes the drive so bumpy. And as you can see here, these are just a couple of examples of the performance and how this highway looks. And as you can imagine, those sort of bumps, even if you drive 100 kilometers an hour, is not really comfortable. Now, another problem with these highways, there's not really a lot of traffic. They straighten those highways. It's actually easy to drive much faster than what the speed limit is telling you to do. And so, yeah, you can actually get a good ride on this road. But the main question was, are these just current problems? I mean, we see infrastructure-related problems all the time. Now, what is climate change doing to it? And that was the main idea of this whole protocol, to go into a systematic way and identify what would climate change do and change to this. Okay, so when you look at climate change, obviously you need to look, first of all, how the climate changed in that particular area. And so we look at air temperature, and then, yeah, obviously there was quite some warming trend over the last 30 years. We had increase in precipitation, both rainfall and snowfall, that was noted. The snow depth changes are very cyclical, so it's not really clear to see trends, but I mean, we saw some increasing snow depth, but snow is not so easy to capture and see these trends. And the timing of the snow, as we heard earlier, is also an important factor for the performance of the highway. But still we have generally more snow, we have generally more rain, we have more rain on snow events, so we have more surface water available in the system, and water is a really important factor when it comes to highway performance. Now, these trends are not any different from other areas that we see in the north, so it was confirming, but we had to identify, first of all, these trends, because they can also be changing locally. So what you then do is you try to come up with a time frame. So you'll say, okay, what's going to happen in 2020, what's going to happen in 2050? So that's, according to the protocol, you can decide your time frame, in essence, the way you want to do it. So we came up with some time and some temperature assumptions for those time frames, because you have to put in a number, and we tried to come up with some changes in precipitation. And as we know, when you change air temperature, we change snowfall, we change precipitation, that results in ground warming, that results in permafrost degradation, and that performs in unstable foundations. So that's just a general scheme, and now we try to quantify it. And that's where the PIVC comes into, and if you haven't heard of PIVC before, it's the Public Infrastructure Engineering Vulnerability Committee, and it's obviously a national engineering assessment of the vulnerability of public infrastructure to climate change in Canada. So it just tries to understand how climate change might affect public infrastructure. And it is a partnership also between Engineers Canada and Natural Resources Canada. So what it does is, you see it here graphically, you basically have your climate event and you have your infrastructure. And then you just try to see how they overlap. How do they affect each other? And you try to do this in a schematic way. So there's the steps you do. First of all, you need to define your problem. So what is your project? What's your project boundary? Then you need to get the data. And that's the first challenging part, is do you actually have enough data? Are they sufficient for your assessment? And then you go into your risk assessment. So you do your risk assessment, you come with a decision. Based on your decision, you decide whether you need to do more engineering assessment on it, and then you might have to go and do a couple of iterations around this before you then come up with conclusion and recommendation. So it's a very prescribed schematic way on how to look at the risks. So what we looked at here is you try to include as many parameters as you possibly can envision. Just don't leave anything out because you think it might not be of importance. Just put anything in, and then the system will tell you what is actually thrown out. So don't prejudge anything at the beginning. So what we looked at is we looked at all the different climate events: air temperature, rainfall, snowfall, fog, ice, hail, frost, ice aggregation, and so on. So there were actually more, and the same on the performance response. So there are different performance responses you have to look at, being it operation, being it emergency services, being it insurances, even coming down to social effects. So you're kind of throwing everything in there, and then you're assessing a risk to each of those different combinations. So you have an event, climate events, then you try to understand what is the consequence of this effect, so this, the severity, and that gives you the risk. So that's the general approach we do risk assessment. So you have the consequence, or you have the probability, you have the consequence, multiplying gives you the risk. The protocol gives you different ways on how to come up with these numbers for severity and for probability. Now, you can do it completely quantitatively and say you have the annual probabilities, or you can do it qualitatively, and that's what we did, because we didn't have enough data to say certain events happen at a certain probability. So you can still go on and say certain probability are negligible or are certain. So you have a range from 0 to 7, and on the same side with the severity, again, it's negligible or it has an extreme consequence in the terms of how severe that effect is. And again, you get from 0 to 7. So you now put your event, you give it a number. Then, so the way the protocol is done is so we as the engineers, we came up with a couple of combinations, a couple of ideas, risks, and then you create a workshop. And during that workshop, which was a 1.5-day workshop, we're bringing in researchers, we're bringing in the stakeholders, we're bringing in the operational planners. So we're bringing in a lot of people, get them into the field, and get the input from them from this workshop. So what do they see? Because you're in the office, you might not see what operational maintenance people see out in the road. So we'll get them, and so from an initial 420 risk combination we came up with nearly 1,500 different combinations during that workshop, just by listening to all these different peoples that have been on the road and seen the road and have been involved in it. And then we managed to reduce it to 1,100. But it's still kind of a lot of combination that has to be considered. Now, what are the challenges when you look at the road, and that's why we have so many combinations, is it's a linear infrastructure. So it's a very long infrastructure. And we have a lot of different foundation conditions. So we have ice ridge conditions, we have bedrock, we have crossings. So there's a lot of different combinations, even from the infrastructure itself, that makes it very challenging. And surface water was another problem. And the as-builts, going back to do we have sufficient data, it's not necessary the as-builts that were available were not necessarily representative of what was actually in the road. And another part which I actually really like here, that's the beaver, because the beavers along the highway have a big influence on surface water. And as you know, surface water can create halics and can create permafrost degradation. So how do you take that little beaver into consideration when it comes to future climate change? So you come up with a matrix that looks similar to this one here. You got lots of different colors. Just going to zoom in a little bit here. And then you're assigning a risk. So you say, oops. So some of them are low, green, medium to high risk. So if we zoom in a little bit here, that's basically how you create that table. You got all the different infrastructure component, as you can see, different culverts on ground ice, different culverts on bedrock, and so on. And you got all the climate effects to the right. So we came up with about 3 or 4 of these tables, and then they got the main points out of it. Now, it's not really surprising, but it's a good thing. So what the protocol gives you is it identified, first of all, which areas are critical, but at the same time, where do you need more data? So you can now tailor your data collection to those areas that are actually critical, and you're not just going out there and keep collecting data after data for elements that are actually not even a risk. And again, not a surprise, obviously when there's ice-rich foundation, that's the most critical part of our highway. And again, increasing ground temperature is highly probable and is probably causing the most risk sections there. So the outcome itself wasn't really a big surprise. and generally, again, to such a general comments is that the road embankment itself is kind of stable. So, I mean, sometimes you think, do we have to change the road embankment itself? And that's not really it. The road embankment structure itself is not really affected by climate change. It's obviously the foundation of it that is more critical. And then increase in maintenance effort is anticipated. And again, it's an outcome for planners to know, okay, due to climate change, one of the consequences is we have to put in more money into maintenance. So you have a tool to go out and tell when you do your budget, you say, okay, we're expecting more maintenance cost. But it also told us that the problems we're seeing and even the high-risk zones are not immediate risks. So you don't have to close the highway and go out there and say, okay, these are really critical zones. So it was, from that part, it was good because you can see all the actions that are required. We still have time to look at those. Now, just some general observation. The workshop was very, very helpful because we, as you saw, we came from about 400 to 1,500 elements. So talking to the people that are involved in the project is the key to success with that sort of assessment. We had good groups, we had good breakout sessions. That was really important. The mix of professionals, as I mentioned, is key. So you don't just put in a couple of engineers back into the room and let them think about the project. Get people out there from operation maintenance, get researchers in there and mix them all up. Time, that was a big issue. It is a big infrastructure, so you need to have more time and sufficient time. And we didn't really do any pre-selection to it, something that could have been done, so we could have given it to the participants early on and then have discussions around critical elements a little bit more. Now, the biggest problem was that it is a 2D matrix system for a long, challenging infrastructure, and that was fitting that long infrastructure, linear infrastructure, into a 2D framework. That was one of the biggest challenges. So generally, was it helpful? Absolutely. I mean, it gave us a lot of ideas, and it allowed us to find critical elements, find data gaps, but as I said, there are limitations of using such a system for linear infrastructure, being it roads, being it pipelines, being it transmission lines. Some initial recommendations we came up with is to extend the workshop a little bit and actually have 2 workshops, to one day, one earlier on, so get people involved, and maybe a second workshop at a later stage where people are more familiar with what's actually going on. And then, yeah, during the workshops, focus on the critical elements and don't end up discussing non-issues for a very long time. That was one of our aims. And for the 3D problem, as I mentioned, that was the biggest challenge, so we should probably look into a 3D in a third dimension so that we're moving our protocol and dividing the road into different sections and creating these matrices for different sections, like a chainage along the highway. So that's kind of the idea. It also helped us designing test sections, and I'm not going to talk about those test sections. They've been installed about a year ago and currently still performing quite good, hopefully. And, but it helped us identifying which are the critical parts and what should we try and actually test out with these test sections. So what do we need to look at when we're trying to improve roads and maintenance out on highways built on warm permafrost. And that's the end of my presentation.